So reaction mechanism 4 has one of these things that I like to think of as shifting gears. And so when you do a reaction mechanism, I want you to ask yourself the question, is it similar to the one that I just did before, or is it completely different and we're doing something new? So just in starting with our starting material here and having a ketone, we can see that there's going to be some things that maybe are similar in the fact that we have this reactive carbonyl functional group. But one of the things that's different is this group that we have attached to our acyl group. So again, this is an acyl group, and the R group that's attached in this case is not a good leaving group. In our previous reaction mechanisms, we had something that was a good leaving group. What's also different here is the nature of our nucleophile. So again, we've got a nucleophile that's not as good of a base as an amine was. So in that case, it's not as strong of a nucleophile. So if we consider that physiological pH is slightly basic, it's reasonable to assume that we've got a situation here where we could have nucleophilic attack here on our electrophilic carbon of our carbonyl, and we do the same kind of chemistry that we saw in our first three reaction mechanisms, which is the formation of a tetrahedral intermediate. So formation of our tetrahedral intermediate here. And one of the things that we need to think about that's similar again to what we saw previously is we're going to do some proton reshuffling. So again, we can have water, or you could use a general base that could deprotonate and return this pair of electrons to that oxygen, alleviating that positive formal charge that we had there. We also can protonate this guy. So again, protonation of our tetrahedral intermediate here is going to generate our neutral hemiacetal And so one of the things I want to make sure to highlight here is the fact that when we have protonation of this group here, that's really the only option that we can have here. Before, when we had the decomposition of this tetrahedral intermediate, we had these electrons that would come down, and then we had a good leaving group here that would come off. But again, we've just highlighted that this is not a good leaving group over here. So the only option when we have our generation of our tetrahedral intermediate is protonation of the tetrahedral intermediate's oxygen to generate an alcohol. And so this is a theme that we'll see when we have what we call sort of a class 2 type of a carbonyl. This is a carbonyl that has an R group attached to the acyl group. So we have something that's not a good leaving group. So either an R group in being a carbon atom and having a ketone, or if this is an aldehyde where this is a hydrogen, that's also not a good leaving group. So after we have nucleophilic attack by our nucleophile and generation of our tetrahedral intermediate, the only option again is protonation of that tetrahedral intermediate. And in this case, it generates, oops, this is not a hemiacetal, apologies there. This is a hemiketal because we started with a ketone. Apologies for that. We start with a ketone here, and so we generate a hemiketal. So reaction mechanism is pretty straightforward with this guy. A couple of comments just to think about, right? This process is called nucleophilic addition chemistry. Again, aldehydes and ketones do not have good leaving groups, so the only option after formation of the tetrahedral intermediate is protonation. So again, see how this is similar yet different from what we saw in reaction mechanisms 2 and 3. We called those nucleophilic addition elimination reactions. So again, that amine nucleophile is going to replace the good leaving group in a two-step reaction. So coming back here, once we got to this tetrahedral intermediate here, we decompose it after we did some proton shuffling, and we'd have this good leaving group in a case of either an acid anhydride or our bioactivated carbonyl compound. Again, the mechanism that I'm going to show you on the next slide is also a plausible mechanism for this reaction mechanism. Again, this time we're going to consider it to be a little bit more of an acidic condition. We're going to protonate the carbonyl oxygen. And so that's going to allow us to increase its electrophilicity and then facilitate the chemistry as, again, an alcohol is typically seen as a weaker nucleophile. So I want you to kind of think about the parallels between this mechanism and then the ones that we did in reaction mechanisms 2 and 3, where we had an amine as a nucleophile. And note that this is going to be very different because if we are in sufficiently acidic conditions such that we can protonate our carbonyl oxygen, that would be also sufficiently acidic to protonate our amine nucleophile, which would mean it couldn't be a nucleophile. And the big picture here is that we can get at that by comparing pKa values. So again, pKa values for protonated amines are 9 to 10. Protonated alcohols are less than 0. So conditions that would be suitable to protonate our carbonyl, again, we'd have to have a very acidic sort of environment to be able to do that, would also be sufficiently acidic to protonate our amine. And so that would, again, be problematic for using an amine as a nucleophile. But it's not sufficiently acidic that is going to protonate our alcohol, having a pKa, remember, of around 15 to 16. So again, no problems with protonation of that alcohol. So I'm just going to kind of highlight by showing the mechanism in more of an acidic solution. So still going to have our carbonyl right here. Now, if we are sufficiently acidic, we can have some hydronium here that we could use to protonate. Let me put my lone pairs of oxygen there. We could use to protonate and make our carbonyl carbon being a better electrophile. So this is again a way to facilitate this chemistry in more of an acidic solution because this is now a much better electrophile. So being a better electrophile is going to allow us to react with our alcohol here. So we're going to see the same chemistry as we saw on the previous slide. Nucleophilic attack on our carbonyl carbon generates a tetrahedral intermediate. Now again, what's different here is we are going to already have this guy be protonated as the alcohol. And now it's just our incoming nucleophile that we need to deprotonate to ensure it is not a good leaving group. So deprotonation of that guy is going to yield the same hemiketal product. So again, another hemiketal. So a couple of things just to sort of highlight here as we're going to see how this has a biochemical application that's going to be very important as we consider sugar metabolism. So when you see something that looks like this, and we've got again a carbon atom that's going to have an alcohol group and an ether group, we have to look next door to the carbon and ask, are you a carbon atom, meaning you originated from a ketone, or are you a hydrogen atom, meaning you originated from an aldehyde? So this is going to become important and actually is going to make reaction mechanisms within this next series of 4 be pretty similar to one another. So again, this mechanism is also plausible if you wanted to consider protonation of that carbonyl oxygen to make it a better electrophile. So again, this is a better electrophile for doing chemistry, and that's important because alcohols are poor nucleophiles. Just a couple comments on sort of the biochemical kind of context for this. So again, hemiacetal formation is found in biochemistry when ketose sugars cyclize. So much as in synthetic organic chemistry, this helps protect the reactive ketone functional group. So just as a little kind of organic chemistry example here, right? If you had a ketone here and you wanted to add a protecting group to that, you could add a diol here. And you'd end up forming, because it's 2 reactive alcohol groups, you'd end up forming this protecting group. So now this reactive functional group is now protected Because remember, a key hallmark of ethers is that they're not very reactive. If we think about what we have in the structure of a sugar, and I'm just going to draw this in a specific way here that will make sense in a few chapters, and I'm not going to worry about the rest of the functional groups that are sort of present on the rest of this. But when we have, in this case, either an aldehyde or a ketone, and we consider a nucleophile that is sort of internal, we have an intramolecular reaction, we could sort of have the same type of chemistry sort of happen here, and we could generate then a ring form here. And this might look familiar because this is basically how we're going to make cyclized sugars. And so this again is a way to protect the reactive functional group of sugars and allow them to not be subject to doing chemistry. So again, this is the ring opening and ring closing that we see with sugars. One other thing to sort of highlight is that we have other potential sources of OH groups. So again, a biochemical application is maybe one of the OH groups comes from a sugar. Another is that we can have an OH group come from serine, threonine, or tyrosine residues, which all have an OH group on their side chain. And so this is a way that we can do the same kind of chemistry to glycosylate proteins, or we add OH groups, or we add sugars to the OH groups of these amino acids. And so if there's one of those amino acids on the surface of a protein, we can actually use it to connect a sugar to it, and that's how we can modify and functionalize proteins. So some really important biochemistry that we'll see with this type of reaction mechanism.